If big f of s is 1 over s plus 1, so let's find the inverse Laplace transform. In other words, we want to find the inverse of, well, the inverse of f of s, which is the inverse of 1 over s plus 1. So this is where we consult that table, right? So we are going to start now with the second column. We need to find something that looks like 1 over s plus 1. Here we go to the table, looking at the second column. There's a lot of E. No, this one, that's cos, sine, cos, sine. They don't look like that. But here is 1 over s plus a. Looks promising. And then on the left side, it says e to the minus at. So if that a is 1, then this would do it. So if a is 1, 1 over s plus 1, we have on the second column, and the corresponding underlying function in the time domain would be e to the minus t. Okay, so in this case, using the table, this is e to the minus t. This is by using table of Laplace transforms. Let me actually now towards the end discuss something more entertaining of how to use this table, because this was kind of boring. Yeah, this. Yeah. No. So there are some cases in which you have to break this up, and this is a method in which you use partial fractions, and you have to make it manipulated in a way in which you can use some of the information that's provided in the table, but it's not obvious right from the start. So let's say this is using partial fractions. So let's say that the function we start with, which is big F of s, has the form s squared plus s plus 1 over s3 plus s. The first thing we're going to notice is that we can rewrite that denominator. Okay, so note that s3 plus s, we can write that as s as a common factor multiplying the quantity s squared plus 1. So we could rewrite that denominator. Okay, and we're going to suppose we have, say, constants A, B, and C, such that s squared plus s plus 1 divided by, this is the original expression, s3 plus s. This is really s squared plus s plus 1 divided by s times s squared plus 1. Excuse me. So we're going to write this ratio as something that looks like a over s plus bs plus c over s squared plus 1. So once we notice that this denominator is the product of s times quantity s squared plus 1, then we want to think of that denominator as being a common denominator that comes out of the addition of two fractions, one of them with denominator s, another fraction with denominator s squared plus 1. So now this becomes of, okay, I need to find what are the values of these constants a, b, and c so that I can really make this work out. Okay, so I'm gonna call this here this one here. I'm gonna call this number 1. Okay, and then let's do a couple of extra steps here. So let's work with this part. So a over s plus bs plus c divided by s squared plus 1. Okay, so now I'm going that direction. So what if I start with the two fractions I really want? I'm going to start with that, and I'm going to do what I normally do if I'm adding two fractions. Common denominator would be s times s squared plus 1. That means I divide that by s, and then here I get a times quantity s squared plus 1, and divide this by the other denominator and get s multiplying that. So we get b s squared plus cs. Now I'm going to call this number 2. So I'm going to equate maybe I should not have called that number 1, you know. This, I'm sorry, that's not what I meant here, because I want to equate, maybe this would be better. Number 1, I want to equate the numerator of the original expression, the numerator which has form s squared plus s plus 1. I'm going to call this, so using the numerator in expression 1 and using the numerator in expression 2, I'm going to set them equal to each other. So equating numerators in 1 and 2. That means that we have s squared plus s plus 1. That's a numerator in expression 1. And that is equal to a plus s squared plus 1 b s squared plus cs. Actually, this right-hand side, I can work out this right-hand side a little bit, right? So I can write a plus b multiplying s squared, and then I have a term, see, I have a term c, s, and I have a term a there. I multiply a times s squared, a times 1, bs squared, and cs, right? So I have to compare the coefficients now. So 1 s squared, we have 1s, and then we have 1. So by equating the coefficients, we have 1 equals 1 plus b, and also 1 equals c, and we also have 1 equals a. So I'm simply comparing the coefficients of this quadratic polynomial on the left-hand side with the coefficients of also this quadratic polynomial on the right-hand side. So A is 1, C is 1. If A is 1, this implies that we have 1 equals to 1 plus B, which implies that B is 0. This gives us exactly the coefficients that we wanted, and so we could write, means that we could write f of s as 1 over s plus 1 over s squared plus 1. And in doing that, the big step here really is to take the inverse Laplace transform of this, which means we're taking inverse Laplace transform of this, inverse Laplace transform of that, and we can easily confirm from the table we have there that inverse of 1 over s is the constant function equals 1, and the inverse of this one would be sine of 1t. So what's the moral of the story? What have we learned from this lesson? Well, it wasn't totally obvious how to use the table in the original form of the fraction. But once we use partial fractions, we could express it as the sum of two fractions, from where we could find each of those as a term on the second column of that table of Laplace transforms, from where it was much more manageable to find out which one is which.